Hey guys, so in the last video, the software got cut off because it allows me to record only 15 minutes per video. So I just have a couple of slides more, and then it will end the topic of International Standard Atmosphere. So as I mentioned in the end of the last video, for the temperature altitude, based on what altitude you're looking at, there are different lapse rates, and there are some altitudes where your temperature remains constant, and you can use the equation which is shown here to determine the temperature at a certain altitude. So in the last video, when I kind of walked you through this kind of short analysis of how you can find temperature at a given altitude, right? So if you can try to find the temperature at 10 kilometers and 20 kilometers altitude at home and put it in your portfolio, that would be great. Again, I just want you to get an idea of this is how temperature varies as a function of altitude, on Earth. So it's a very important, we'll talk about the importance of this in the next couple of slides. Okay, so similar to temperature altitude, there's what is called pressure altitude. So pressure altitude is nothing but change in pressure as a function of altitude. So as you know, as you go up the altitude, the pressure goes down, and when you go to space, you don't have any pressure, so it's an empty vacuum, right? So but there's a certain trend to the change in pressure as a function of altitude inside the atmosphere. And if you're flying an airplane at a certain altitude, you need to be aware of what that ambient temperature is, so that you can calculate your lift and drag measurements the right way. Okay, so if you look at the equations up to 12 kilometers or up to tropopause, there is an equation for pressure which is shown in here. Okay, so basically this is P. If you want to find a pressure at a certain altitude, H, then you can take the pressure at sea level, which is around 101 kilopascal, and you multiply that times 1 minus 0.0065 times altitude that you're interested in, divided by the temperature at the sea level, which is around 288.15 Kelvin, to the power of 5.2561. Again, the trend that you saw in the temperature and the pressure was determined through experimental investigations. I mean, these are not just equations. These numbers are obtained by having a weather balloon and taking data across the range of altitude. So that's how they got this information. This is not all mumbo jumbo. So this is how they actually the parameters vary. So, and after 12 kilometers and above, your pressure actually changes the trend. So if you want to calculate pressure above 12 kilometers, then you use this equation shown in here. So where instead of using sea level as a reference point, you use troposphere or tropopause as a reference point. So P above, if you want to find pressure above the tropopause, then you multiply the pressure of the tropopause, which is around 22,632 pascal, times the exponent of G. It's a gravitational constant, G 9.81 meters per second square, and then R is a gas constant. It's around 287 joules per kilogram Kelvin, and temperature at the tropopause is around 216.65 Kelvin, and the height you're interested in minus the height of the tropopause, which is around 11 kilometers. So again, these two are the equations which you can use to determine pressure, or the ambient pressure, at that given altitude. Okay, so now we saw pressure, we've seen temperature and pressure, and what's left is a density. Density also varies similar to pressure. There's not so certain equation in there, although you can use the ideal gas assumptions to calculate density from pressure, but we are interested in the trend. So as the altitude increases, your density actually drops. So similar to pressure. Now, the reason why I said temperature is very, very important is because temperature is directly related to the speed of sound. So if you remember our discussion on a high-speed flight, the equation for speed of sound is actually A equals square root of gamma R and T. right? Gamma is a specific heat ratio, so 1.4 for air. R is a gas constant, so 287 joules per kilogram Kelvin, and T is a temperature. So as you can see, the speed of sound is actually changes with temperature. Now, why this is important? It's important because our Mach number of the airplane is divided, it's defined by velocity of the airplane divided by the speed of sound, right? So what that means is that your airplane can fly at fixed certain velocity along the different altitudes, but their Mach numbers will be different. Okay, so if your airplane is flying at around 500 miles per hour in at around 5 kilometers in altitude, then your Mach number will be around 0.8 or 0.7, 0.8. But when you're flying at 100 kilometers or 85 kilometers altitude right here, then your Mach number will be much higher because your speed of sound is much lower than what you have in at lower altitudes, right? So that means your shock will form very easily at lower velocities of the airplane as you fly higher, right? So this is one of the reasons why we need to be very, very important. We need to be aware of these variations in temperature because it directly affects the flow characteristics around an airplane. Now, this is one of the reasons why the X-15, the experimental flight, actually flew at higher atmosphere, because they can get to high Mach numbers very easily by having a low velocity. That means, low thrust, right? So that's one of the reasons why, most of the high-speed experimental airplanes like to fly at higher altitudes. But with higher altitudes comes a lot of challenges. The cabin has to be pressurized. You need to wear a spacesuit. And you need to take care of temperature effects. There's a lot of other things, but it allows us to investigate the high speed aerodynamics at a relatively lower cost. So that's all I wanted to say about international standard atmosphere, and I hope you guys find this topic a little bit interesting, because I think it is. It's important for us to know how these parameters vary. So if you can listen to this video and do a quick summary and reflection on the portfolio, that would be great. All right. Have a good Thanksgiving break, guys. Hopefully, you guys use the time for the class to work on your projects. We need to, once we get back from the break, then I'll catch up with each and every group and make sure that you guys are on the track to complete the projects by 13th of December. All right. All right. Have a wonderful break. Happy Thanksgiving, and I'll see you when you guys get back.